Good morning. I wish I could be there live virtually, and I want to thank the workshop conveners for this invitation and for allowing me to send you this recorded presentation. I'm really going to miss the discussions at the end of this session and tomorrow as well. Um, but hopefully Carlos will have my slides, and if there are any questions, um, I'm sure he can answer them. So I'm going to give a quick overview of sea ice changes, starting with circumpolar sea ice changes and really the most recent changes, and then what we can learn from the sea ice changes observed along the Antarctic Peninsula. So I'm going to hide my recording and or I'm going to hide my my picture here and see if this works. Okay. So here we're showing the Antarctic sea ice extent anomalies, and this is from Zachary Labe's website. And many of you know this time series, setting the context, but in blues, we have positive sea ice extent anomalies, reds negative. And so we saw this in the beginning of the satellite record, this overall weak increase until about 2010 to 15, record high sea ice extents, and then quite quickly a transition to record low sea ice extents. And many in the community are suggesting that there's been a state shift in sea ice and perhaps in ice ocean coupling specifically. And why that is being questioned is because more recently we've been seeing these dramatic record lows in winter. So previously it was mostly record lows in summer, and now we're seeing winter. And these now are the daily sea ice extent anomalies throughout the season. And what's highlighted here is those record lows in 2023, but they are continuing to persist up until current day, though not quite as dramatically. So what do the spatial patterns look like in this transition from weak increasing trends to now decreasing trends? Well, spatially, as many of you know, we had this very strong regionality so what I'm showing here are trends in the ice season duration. In general, reds are to shorter seasons, blues are longer seasons by up to 3 months. And we saw very shortening of sea ice seasons and sea ice extent in the peninsula and Bellingshausen, contrasting with those increases in the Ross Sea, but with a net circumpolar wide increase. And then with that shift in 2015-16, mostly circumpolar wide sea ice decreases. We have this interesting feature in some of these coastal regions. I'll get back to this, but this is largely shifts in the Amundsen Sea low. And on that point, so what I'm showing you here now are the trends in sea level pressure and shading. So here we're having decreasing trends in this Amundsen Sea low area, and that was very pronounced in the first half of the record. And as we transition to the second half of the record and this new state that's being proposed is that we basically see low sea ice pressures, sea level pressures everywhere, a weakening of this Amundsen Sea low towards the east because it has shifted west. And overlaid on top of that are the sea ice drift patterns. And what this is, there's a lot of detail here. I'm not going to go into all of that, but basically most of the sea ice changes in the earlier part of the record could be related to wind-driven changes. Not everywhere, but most places. And in the recent shift of decreased sea ice, we see weaker coupling with atmospheric forcing. And so what does the underlying ocean look like? And this is showing you the upper ocean will surface to 500 meters of temperature anomalies from Argo float observations. Importantly, this is from the 55 south to 65 south. So it doesn't quite go to the coastal regions or on the continental shelves, and that's a big gap in our and ocean observations and in our understanding really with regards to sea ice coupling. But what we're seeing is in general this shift, this now is kind of the change point in 2015-16 of fresher surface conditions, fresher and cooler to saltier and warmer. And how these are also kind of changing the subsurface environment as well. What's not really too pronounced here, but we were seeing a subsurface buildup of ocean heat. And then when this episode happened, we weakened ocean stratification, and this has been well documented, mostly an atmospheric driven event. And this weakened that stratification and allowed greater salt and heat from below. And this has been proposed as what's driving this new state shift in sea ice, a greater influence from ocean heat from below. So if we want to put this in a conceptual view, this is a progression that was described by Kinza-Hemmick et al. And so what we're going to start with, this is post-shift minus pre-shift. So in general, what we're seeing here in the blues are a shift to shorter ice seasons in the recent period. We're also seeing a shift to generally thinner sea ice, but there's a lot of uncertainty in this, and this is a combination of satellite and model um, observations. And with shorter sea ice seasons, thinner sea ice, we have earlier spring sea ice retreat dates most everywhere. Again, this is an interesting change, and this is related to that westward shift of the Amundsen Sea low. And then with the shorter ice seasons, we have longer open water seasons, greater upper ocean heat content here, showing the maximum sea surface temperatures, and then a later sea ice advance. So this is the sequence. We are proposing that there is both a wind-driven component, which is changing the seasonality of the sea ice, but then there's also an ocean thermal component that could be changing the sea ice thickness. So what can we learn about these processes at a more specific or detailed investigation? And so we're going to look at the Western Arctic Peninsula. And here I'm just showing you in a slightly different format plotted by Carlos Moffett. Thank you very much, Carlos. But showing you what you saw previously in the upper figure, the Antarctic wide sea ice extent changes and the anomalies. So this gradual increase to record highs, record lows. But what was the peninsula doing? Well, the peninsula, as you saw in that map of ice season duration, had been trending down to shorter seasons, decreasing sea ice extent. We had this interesting recovery period when the first shift happened, Antarctic wide, but we've since resumed this decreasing sea ice trend. Now, this shift, again, I've hinted at it, but it's kind of related to the changes in the longitudinal position of that Amundsen Sea low. I can't go into detail, but perhaps the previous speaker did. So we're going to delve into some ocean observations and couple that with a modeling framework. So here I'm just showing you the Palmer Long-Term Ecological Research Grid west of the peninsula, really highlighting in this red dot a mooring location. And we have observations from 2007 to 2011. And we then assimilated those ocean observations into a very simple 1D vertically coupled model. And I'll show that in the next slide. But what we're really asking the question here is this seasonal progression of sea ice ocean interactions. And so in winter, as sea ice grows, we create this winter water, which overlies that warm circumpolar deep water. And in summer, the sea ice melts, we stratify the surface with warm, fresh water. That winter water gets pushed into subsurface and is very vulnerable to both top-down forcing and bottom-up forcing. And so that's the question we're asking. So we're taking this very simple 1D vertically coupled ice-ocean model, and here I'm showing you a simulation where we just do surface forcing. And so on the right, you're seeing the temperature progression from April to February. So initially, that warm surface layer with the subsurface winter water layer and that warm circumpolar deep water. As the surface cools off and we start to grow sea ice, we then have the situation where we have this winter water, which actually never goes away. So that's a problem in this 1D modeling framework. But it does capture the onset of sea ice growth, which is shown over here from July to February. As that thickens, as the winter water becomes well established, and you're capping off that heat from below, and then you have snow cover on top. And of course, the sea ice never melts. So obviously, we're not capturing both the bottom up and the top down forcing. So we played around with this, and we first assimilated the ocean observations. See if I can make that go away. Hopefully you're not seeing that, but so when we assimilate the mooring observations, we see, first of all, there's a lot more high frequency variability, both in that modified circumpolar deep water temperature as well as vertical excursions. And when we assimilate those ocean observations, we see we get a quite different profile in sea ice thickness with these melt episodes related to these vertical excursions. And so that these vertical excursions are releasing heat and affecting the basal melt of the sea ice, so basically affecting the sea ice thickness. Now, if we only assimilate the satellite observed sea ice concentrations, which we know in this area are very wind driven, we see, of course, a very realistic sea ice cycle, right? Especially this year, it was very short. So if we impose that on the model and we let the simulated ocean do its thing, we see that it's a short season, but relatively thick, as thick as it is up here. But if we add the ocean back in, we see that it does act to thin that shorter ice season. And so that was a very quick summary of this paper, but the key take homes is that the assimilated ocean temperatures always produce thinner sea ice when the picnic line was shallow. So every time those vertical excursions happen, by the way, this is a very eddy prone area. So the mooring was intentionally put there to observe these eddies passing by. And then every time the picnic line went deeper, we had the opportunity to grow thicker sea ice. And then when we assimilated the sea ice concentrations, which brought in this lateral advective component, we always, because of the lower sea ice concentrations in general, created greater surface heat fluxes and thinner sea ice. And so that's just giving an idea of the top down versus bottom up forcing potential. And in this paper, those heat fluxes and heat budgets were quantified. So this is just giving you a quick conceptual view. So given everything that we just described, so the proposed shift to this new CA state would suggest that we have indeed evidence that indicates thinning of sea ice by these episodic ventilations of circumpolar deep water. This needs to be resolved most everywhere in the Southern Ocean using, really on the continental shelf where we have very little ocean observations. And as a result, though, we generally get thinner sea ice during the winter. That thinner sea ice is more vulnerable to an earlier sea ice meltback. And then we have a longer open water season that is exposed to greater wind forcing, so we can weaken that summer restratification. And then if that happens, we can then progressively have greater upper ocean heat content that is gained throughout the summer, that weakens the ocean stratification, that then leads to subsequently shorter winter ice seasons with thinner ice overall, and then repeating the cycle to earlier spring meltbacks. So that is where we are currently. But we still have many questions. And for example, how well do we really know the atmospheric versus the oceanic changes, and therefore the strength of those drivers on these sea ice changes? And I would redirect you to the talks by Sergi and Brendan for some insights there. And then, of course, this competition between warming versus freshening at the surface. And I would encourage you to look at the talks by Michael and Jack. What I didn't touch on this talk, but also we're actively looking at the influence of wind and waves on sea ice, extent and concentration changes, the modulation of the thermodynamics by snow loading, and really, of course, ultimately being able to better decipher anthropogenic versus natural variability. I hope this recording worked, and I thank you again for this opportunity.